Sagittarius A is, by almost every measure, remarkably quiet. For a supermassive black hole, an object containing 4 million times the mass of our Sun, anchoring an entire galaxy of hundreds of billions of stars, it produces almost nothing. Occasional small flares, brief faint pulses of X-ray and infrared radiation that last minutes and then fade, compared to the supermassive black holes at the centres of other galaxies, which blaze with the light of entire star clusters as they consume surrounding matter. Sagittarius A is practically invisible. Astronomers have a term for black holes like this: sleeping giants. For decades, that quietness defined how we thought about the centre of our galaxy. Whatever was there, whatever object anchored the Milky Way and held its hundreds of billions of stars in their orbits, it was dormant, passive, a gravitational anchor with almost nothing left to consume, sitting in relative stillness at the heart of everything. That picture felt settled, and then, in January 2026, a team led by Michigan State University researcher Stephen DiKerby published findings from a telescope that had been staring at a molecular cloud near the galactic centre, a vast cloud of gas floating in the darkness a few hundred light-years from Sagittarius A itself. What they found inside that cloud's X-ray glow rewrote the recent history of our galaxy's centre entirely. The cloud was glowing. Not with its own energy. Molecular clouds don't produce X-rays on their own. It was reflecting something. Light that had travelled from Sagittarius A struck the cloud and bounced back toward us, arriving at our telescopes not as fresh radiation from a current event, but as a delayed signal from something that happened long ago, an echo, a light echo from the past. And what the echo was telling them was this: Sagittarius A, the sleeping giant, the quiet anchor, the object that produces almost nothing detectable on a day-to-day basis, had, sometime within the past few hundred to 1,000 years, released an explosion so powerful it still hadn't finished travelling through the surrounding space. During that event, it glowed 10,000 times brighter than it does today, not gradually, not as a slow increase in activity. A violent, sudden outburst, the kind associated with a black hole actively consuming large amounts of surrounding matter, the kind we see in distant galaxies and classify as some of the most energetic events in the observable universe. Here, at the centre of our galaxy, within the last 1,000 years. This didn't happen in the deep past, in the billions of years before Earth existed, before life existed, before the solar system formed. This happened recently, in human terms, extraordinarily recently. Somewhere between the time of the early medieval period and the time of the Renaissance, something at the centre of the Milky Way erupted with a violence that dwarfs anything we've ever detected it producing in modern observations, and nobody knew, not because the evidence wasn't there, because the evidence was still travelling toward us, bouncing off molecular clouds, arriving centuries late, waiting for a telescope precise enough to read it clearly. That telescope launched in 2023, and what it heard has changed everything we thought we understood about the recent history of our own galaxy. To understand why the echo finding is so significant, you need to understand just how quiet Sagittarius A actually is right now. Most people, when they imagine a supermassive black hole at the centre of a galaxy, picture something actively consuming, a violent luminous engine surrounded by blazing and falling matter, jets of energy firing outward along its poles, the surrounding space lit up by the violence of its appetite. That image isn't wrong as a general description of supermassive black holes. Many of them look exactly like that. Sagittarius A doesn't. In other galaxies, supermassive black holes in active feeding phases are classified as active galactic nuclei, AGN. Their energy output can outshine the combined light of every star in the galaxy surrounding them. Quasars, the most extreme version of this phenomenon, are so luminous they were initially mistaken for stars when first detected despite being billions of light-years away. The energy comes from matter falling toward the black hole, heating up as it compresses and orbits in an accretion disk, releasing enormous amounts of radiation before crossing the event horizon. Sagittarius A has almost none of that. Its accretion rate, the amount of matter it's currently consuming, is extraordinarily low. The material available to fall into it has largely been depleted or dispersed. What little does fall in produces only faint, brief flares, spikes in X-ray and infrared emission that last minutes and then disappear, the astronomical equivalent of a campfire rather than the industrial furnace you'd find at the centre of an active galaxy. This makes Sagittarius A something of an anomaly. Given its mass, 4 million solar masses, substantial even by supermassive black hole standards, it should, statistically, be more active than it is. The galactic centre is not a quiet environment. It's one of the densest, most energetically active regions in the entire Milky Way, packed with young, massive stars, giant molecular clouds, intense magnetic fields, and the remnants of past stellar explosions. And yet, the object at the centre of all of it produces, by the standards of its peers, almost nothing. For decades, this quietness was attributed to a simple explanation. Sagittarius A star had run out of easily accessible food. The gas and dust that once fed it had been consumed or blown away. What remained was too diffuse, too sparse, too far from the event horizon to fall in at any significant rate. The sleeping giant had simply exhausted the local supply. That explanation felt adequate, and it produced a specific picture of the galactic centre's history, one in which Sagittarius A star had been gradually winding down over millions of years, growing quieter and quieter as its food supply dwindled, settling into the near dormancy we observe today. What the XRISM findings demolished was not just that timeline. They demolished the assumption that what we observe today, this quietness, this near-total dormancy, is representative of even the recent past. It isn't. The sleeping giant wasn't always sleeping, and the evidence of when it last woke up has been drifting through our own galaxy, waiting to be read, for centuries. Before you can understand what XRISM detected, you need to understand what it was looking at. Floating in the region around the galactic centre, within a few hundred light-years of Sagittarius A itself, there are enormous clouds of gas and dust, dense, cold, vast structures containing millions of solar masses worth of molecular hydrogen, carbon monoxide, and dozens of other compounds. Astronomers call them molecular clouds, and the ones near the galactic centre are among the largest and most studied in the Milky Way. They're not glamorous objects. They don't glow on their own. They don't produce dramatic visible light or the kind of imagery that ends up on the covers of science magazines. In most wavelengths, they're simply dark, absorbing light rather than emitting it, blocking our view of whatever lies behind them. But in X-rays they do something extraordinary. When a powerful source of X-ray radiation, a flaring black hole, a gamma-ray burst, an exceptionally energetic stellar explosion, illuminates a molecular cloud, the cloud doesn't just absorb that radiation, it scatters it, reflects it. The X-ray photons interact with the iron atoms embedded in the cloud's dust, causing those atoms to fluoresce, to re-emit X-rays at specific characteristic energies. The result is a cloud that glows in X-rays, not because of anything happening inside it, but because it's acting as a mirror, reflecting and re-emitting radiation that originated somewhere else, at some other time, and has only now caught up with the cloud after travelling across the intervening space. This is what astronomers call X-ray reflection nebulae, and they have a property that makes them extraordinarily useful for studying the past. Because light travels at a finite speed, and because the molecular clouds around Sagittarius A sit at varying distances from it, different clouds receive the same outburst at different times. A cloud sitting slightly further from Sagittarius A than another will receive the same X-ray pulse slightly later, delayed by however long it takes light to cross the extra distance. This means the clouds around the galactic centre are not all reflecting the same moment in Sagittarius A's history. They're reflecting different moments, a sequence of snapshots, spread across time, each cloud showing us the galactic centre as it was at a slightly different point in the past. Together, they form something remarkable, a timeline, a record, a fossil light archive of everything Sagittarius A has done within the last few thousand years, written in reflected X-rays and stored in the molecular clouds surrounding it. Previous telescopes had detected hints of this, faint X-ray glimmers from molecular clouds near the galactic centre, suggestive of past activity, but never clear enough to be definitive. the energy resolution of existing instruments wasn't sufficient to examine the fine structure of the reflected radiation, to distinguish precisely what had produced it, whether it was a past outburst from Sagittarius A or some other source like cosmic rays interacting with the cloud material. The answer was always frustratingly ambiguous. Until XRISM pointed at the clouds with a precision no previous telescope could match, and the ambiguity disappeared. XRISM stands for X-ray Imaging and Spectroscopy Mission. It launched in September 2023, a partnership between NASA and the Japan Aerospace Exploration Agency. In the hierarchy of space telescopes, it doesn't have the cultural profile of the James Webb Space Telescope or the historical legacy of Hubble. It doesn't produce the kind of sweeping, colourful, deep field images that spread across social media and end up printed on posters. What it does is something far more precise and far less visually dramatic, and for certain scientific problems, far more powerful than any imaging telescope ever built. XRISM measures the energy of individual X-ray photons with a precision that no previous space telescope has come close to achieving. To understand why that matters, you need to understand what spectroscopy actually does. Every atom, every ion, every element in the universe interacts with light at specific, characteristic energies. When matter is heated, compressed, or irradiated, it emits or absorbs X-rays at wavelengths that act like fingerprints. Unique signatures that tell you exactly what the emitting material is, how hot it is, how fast it's moving, and what physical processes are acting on it. The more precisely you can measure those energy signatures, the more information you can extract from the light. Previous X-ray space telescopes could distinguish the energy of a photon to about 1 part in 10, or in the best cases 1 part in 100. That's like being able to tell that a sound is roughly a middle C, in the right ballpark, useful for broad classifications, but missing the fine detail. XRISM resolves photon energies to 1 part in 1,000. That's the difference, as the researchers themselves described it, between a Polaroid photograph and a high-definition Technicolor image. The same scene, the same subject, but one reveals details the other simply cannot show. For the molecular clouds near the galactic center, this precision made all the difference. Previous telescopes had detected X-ray emission from these clouds, but couldn't determine its origin with certainty. The energy signatures were too blurry, consistent with reflection from a past Sagittarius A outburst, but also consistent with other explanations. Cosmic rays, high-energy particles travelling through the galaxy, can also cause molecular clouds to emit X-rays when they collide with cloud material. Distinguishing between X-rays produced by reflection and X-rays produced by cosmic ray bombardment requires precisely the kind of fine energy resolution that previous instruments lacked. XRISM has that resolution. When Stephen DiKerby's team pointed it at the molecular cloud near the galactic center and examined the X-ray spectrum in detail, measuring the energy of individual photons with 1 part in 1,000 precision, the fine structure of the emission told a clear story. The energy signatures were wrong for cosmic rays. They were exactly right for reflected X-ray radiation from a powerful past outburst. The ambiguity that had frustrated galactic center researchers for years, the tantalizing hints that something had happened in the recent past, visible in the faint glow of the surrounding clouds, but never definitive enough to confirm, collapsed into certainty the moment XRISM's data came through. The cloud wasn't generating its own X-rays, it was reflecting someone else's, and the someone else was Sagittarius A. Here is what the data showed. Sagittarius A, the object at the centre of our galaxy, currently so quiet that its day-to-day activity barely registers on our most sensitive instruments, released a violent X-ray outburst sometime within the past few 100 to 1,000 years. During that event, it glowed 10,000 times brighter than it does today in the X-ray range. Not twice as bright, not 100 times brighter, 10,000 times. To put that number in context, on its most active days right now, Sagittarius A produces brief flares, spikes in X-ray emission that last minutes, peak at a few times its baseline output, and then fade. These flares are detectable but modest, the kind of activity that requires sensitive instruments pointed specifically at the galactic center to notice at all. What happened within the last 1,000 years was not a flare in that sense. It was an eruption. A sustained outburst of the kind associated with a black hole actively consuming large amounts of surrounding material. The kind of activity that, in other galaxies, produces the blazing luminosity of an active galactic nucleus. The kind of event that, had it occurred in a galaxy we were observing from a safe distance, we would classify as one of the most energetic phenomena in the observable universe. It happened here, at the centre of our own galaxy, within the last 1,000 years. The timing matters in a way that's difficult to fully process. 1,000 years ago, human civilization looked completely different. The Crusades hadn't begun. The Mongol Empire hadn't yet formed. The Renaissance was 5 centuries away. Every major religion on Earth was in a substantially different state than it exists today. Every nation, every border, every language that defines the modern world was either absent or unrecognizable. And while all of that was happening, and while human beings were living their lives in a world we would barely recognize, the object at the center of the Milky Way was releasing an explosion so powerful that its light is still traveling through the galaxy, still bouncing off molecular clouds, still arriving at our telescopes today. We weren't there to see it happen. We're seeing it now, centuries late, because the universe keeps records. What caused the outburst? The most likely explanation, according to the researchers, is that Sagittarius A consumed a large amount of surrounding material in a relatively short period. The activity is described as characteristic of hungry black holes, objects that are actively absorbing matter at a significantly higher rate than normal, the surrounding gas heating up as it spirals inward, releasing enormous amounts of radiation in the process. This implies that 1,000 years ago, there was significantly more gas and material in the immediate vicinity of Sagittarius A than there is today. Something drove that material inward. Perhaps a molecular cloud drifting too close to the galactic center. Perhaps the tidal disruption of a star or a dense concentration of gas by the extreme gravity of the central object. Whatever the trigger, the result was an object that had been quiet for an unknown period suddenly consuming material at a rate that produced an X-ray luminosity 10,000 times its current output. And then, at some point, it stopped. The gas was consumed or dispersed, or the infall rate dropped below the threshold needed to sustain the outburst. Sagittarius A star went quiet again, and has remained quiet ever since. The light from that outburst travelled outward from the galactic centre in all directions. Most of it dispersed into the galaxy, too diffuse to detect. But some of it struck the molecular clouds floating in the surrounding region, and those clouds, acting as cosmic mirrors, reflected it. Not all at once, each cloud reflecting the light as it arrived, the reflection depending on the cloud's distance from the original source. Some of those reflections are reaching us now. Others reached us decades ago and have already passed. Others haven't arrived yet, still travelling toward us. The delayed echo of an explosion that ended centuries ago, still propagating outward through the clouds of the galactic centre. XRISM caught one of those reflections, measured it, characterised it, confirmed it, and in doing so, gave us the first clear, unambiguous evidence that the sleeping giant at the centre of our galaxy has a violent recent past that nobody knew about until now. The immediate scientific implication is straightforward. Sagittarius A is not as dormant as we thought, not over the timescales that matter for understanding how our galaxy actually behaves. The picture of a gradually winding down black hole, settling into permanent quietness over millions of years, needs to be revised, because the evidence now shows it was capable of a violent major outburst within the last 1,000 years, and capable of returning to near-total quietness just as quickly. That's not a gradually declining system. That's a system that can switch. And if it switched once within the last 1,000 years, the question that follows immediately is uncomfortable. How many times has it switched before? The molecular clouds around the galactic centre can only preserve light echoes for so long before the reflected signal disperses below the threshold of detection. The current findings give us a window into the last few thousand years of Sagittarius A star's activity, a narrow slice of its multi-billion-year history. What happened before that window is effectively invisible to this method, but the finding implies that what we've been calling Sagittarius A's quiet phase may not be a permanent state at all. It may be an interval, a period of reduced activity between outbursts, one of many that have punctuated the object's history across billions of years. The current quietness isn't the end state of a dying engine. It's a pause. How long the pauses last between outbursts we don't yet know. How large the outbursts can get we don't yet know. Whether the 1,000-year-old event was typical or exceptional in its intensity, we don't yet know. There's also a broader implication for how we understand galactic centers in general. Sagittarius A has long been treated as a model for studying low-activity supermassive black holes, objects that have consumed most of their surrounding material and settled into near dormancy. The assumption was that its current state was representative of its recent history, and that studying it in its quiet phase would tell us something general about how supermassive black holes behave as they age. That assumption is now compromised. If Sagittarius A can produce an outburst 10,000 times its current output within 1,000 years, and then return to near-total dormancy, then its current state is not representative of its recent history at all. It's a snapshot of one phase of a more complex, more variable, more dynamic system than anyone modelled. Every conclusion drawn from studying it as a typical quiet black hole now carries a caveat, and then there's what this means for the future. If Sagittarius A has woken up within the last 1,000 years, there's no reason in principle why it can't wake up again. The galactic centre is not empty. There are molecular clouds, dense gas structures, and stellar remnants within range of its gravitational influence. If the right amount of material drifts close enough, infall could begin again. The researchers are careful not to predict a timeline. Astronomical events of this kind unfold over timescales that make human planning irrelevant. An outburst could be thousands of years away, or millions. The data doesn't say. But dormant and permanently dormant are not the same thing, and for the first time we have direct evidence from our own galaxy that the object at its centre knows the difference. There is something specific about this story that separates it from most discoveries in astronomy. Most of what we learn about the universe comes from looking outward, at objects far away, in other galaxies, in other cosmic environments. We study distant black holes, distant supernovae, distant galaxy clusters, and draw conclusions about the universe's general behaviour from what we observe at a safe remove. This is different. This is our galaxy, the structure we live inside, the system whose gravitational architecture determines where our solar system sits, how it moves, what it's exposed to over geological and astronomical timescales. And we just learned that its centre has a recent history of violence that nobody knew about until a telescope launched 3 years ago finally had the precision to read it. Think about what that means in terms of the record the universe keeps. The outburst happened. The light travelled outward. It struck the molecular clouds surrounding the galactic centre and reflected, not as a deliberate signal, not as anything intentional, just as the automatic consequence of light hitting matter and scattering. The universe doesn't archive its own history on purpose, it simply obeys physics. And physics, in this case, preserved the record of an event that happened centuries ago in the reflected glow of a gas cloud that nobody was specifically looking at until recently. We didn't find this because we knew what to look for. We found it because we built an instrument precise enough to read what was already there, what had been there for centuries waiting in the X-ray glow of a molecular cloud drifting in the darkness near the galactic centre. 1,000 years ago, the object at the centre of our galaxy erupted. At that moment, somewhere on Earth, people were living their lives with no knowledge of what a galaxy was, no concept of a black hole, no framework for understanding that the faint band of light they could see, crossing the night sky, was the edge on view of the structure they were embedded in. The idea that something at the centre of that structure had just released an explosion 10,000 times brighter than its baseline output would have been not just incomprehensible, it would have been unaskable. The question itself didn't exist yet. The light from that explosion has been travelling ever since, through the galactic centre, through the molecular clouds, across the centuries, arriving at our instruments now, not because it was sent to us, not because the universe intended for us to receive it, but because light travels and matter reflects, and we happen to build the right telescope at the right time and point it at the right cloud. There will be more echoes, other molecular clouds at different distances from the galactic centre, are still receiving the reflected light from that same outburst. Each one a slightly different timestamp, a slightly different frame from the same ancient event. Future observations with XRISM and instruments that haven't been built yet will read those clouds and fill in more of the picture. The timeline of what happened, how long it lasted, how intense it was at its peak. All of that is recoverable, written in X-rays, preserved in gas clouds floating in the darkness, a few hundred light years from our galaxy's centre. The record isn't complete yet, but we've started reading it. The object at the centre of our galaxy screamed centuries ago into the darkness. It didn't know we were here, it didn't know anyone would ever be here. It didn't know that the light from its outburst would one day reach a small blue planet orbiting an unremarkable star near the edge of the galaxy it anchors, where a species that hadn't existed when the light left would build instruments sensitive enough to hear it. It just erupted. And the universe, indifferent as always, kept the record. We finally found it.